There will come a time you're going to wonder how power supplies work. And it is in theory, a voltage that going to be an output in a certain supply is not that regulated and not that exact. For this session, a problem solved, we're going to tackle power supplies in a linear discrete way. Hello, what's up guys? Sergio again here, and for tonight we're going to discuss discrete transistor voltage regulators. Okay, so just to give you a brief recall of what's happening, okay, so if we're going to recall what is the blocks that compose for a voltage regulator, okay, so we know that for a voltage regulator, okay, so we have here the AC, okay, so that could be direct IC converting to DC or something like that, okay. So, but what's common is using AC to DC conversion, that is a voltage regulation in a linear manner. So, that would compose of several blocks. For the first block, so we have here an AC source, followed by a rectifier, followed by a filter, followed by the voltage regulator, and lastly, that would be our DC output. So for this edition of Problem Solved, we're going to discuss about discrete transistor voltage regulators. So for discrete voltage regulators or discrete transistorized voltage regulator, so discrete transistorized voltage regulator. So we have two configurations for this. We have the series and the shunt. But for now, let's have the common configuration, which is the series. Okay. So for the series transistorized voltage regulator, okay, the block of the circuit is composed of the following. So we have the voltage input, okay. So the voltage input goes to a control element. The control element is mandated by a voltage comparator. The voltage comparator keeps the voltage in level. And the voltage comparator is controlled by a voltage reference or reference voltage. Okay. Then it's 4 blocks. Okay, so we have here a sampling circuit. And lastly, we have the voltage output. Analyzing the circuit that involves voltage regulators, okay, requires you to have a prerequisite or the knowledge of circuit analysis. That's why it's essential you have knowledge of circuit analysis before you go on this topic. Have the word erase. Okay, so we're going to have here a sample problem. Okay. So let's have here a series voltage regulator circuit using a zero diode and a transistor. So a usual circuit, okay, so we have right here sample problem. Okay. So a usual circuit or a usual voltage regulator circuit is configured or connected in a common base connection. Okay, so that will be in BJT. We're calling your knowledge in BJT, okay. We know that if you have a common base connection, okay, that would be the output is taken in the emitter and the input is fed to the collector. Okay, so common base, if you want this, let's recall. So for common base, okay, input is in a collector, and the output is in the emitter. A usual circuit or a usual voltage regulator circuit using transistor and Zener diode is drawn like this. So that would be like that. Okay. So we have here the transistor. Transistor. Okay. So we have here our input voltage, Vin. That would be our Vout. Okay. Then we have here a Zener diode. Okay. Then this is grounded. Okay. As what I've said, it's common based. Then we have here a little resistor, okay, prior for the voltage output. And this would be a feedback configuration. Okay, something like that. Okay. So let me call this as RC. Okay. Let me call this as RE. Or rather, load resistor RL. Okay. Sorry, let me erase that first. So this would be our RL. So then let's inject some parameters. Okay, sorry for that cut. Okay, so I ran out of films. Okay, so as you can see, I've now injected all the values. Okay, so I ran out of film. So sorry for that cut. Okay, so for this particular circuit, we're asked to calculate the output voltage and the Zener current. Okay, so by circuit analysis, okay, as you can see, I can directly loop this. Okay. So that I can say that our output voltage would then be equal to the voltage across the Zener diode minus, okay, the bias voltage of the transistor VBE. Okay. So there would be a hidden parameter here. Okay. So we know that the voltage across the emitter and the base, or what we call as the VBE, is simply equal to 0.7 volts. Okay. So if we're going to loop that, we can say that the output voltage VO would then be equal to the voltage Zener, or the Zener voltage 12 volts, minus VBE, which is equal to, by default, 0.7 volts. Okay. Subtracting the two, so we'll have 11.3 volts. And that would be our output voltage. Okay, now, we also need to find the Zener current. But how do we find the Zener current? Okay. So to find the Zener current, we need first to analyze the whole circuit. Okay. But how? Okay. So we need the drop for every part till we arrive at the last part of the circuit, at the sampling circuit part. Okay. So how are we going to analyze this? Okay. So we're going to solve for the voltage across the collector to the emitter, VCE. Okay. So to solve for VCE, that is simply the voltage input minus the voltage output. Okay. And that would give us 20 volts minus 11.3 volts. Okay. So subtracting to 2, so that will give us 8.7 volts. Okay. So that would be the voltage across the collector and the emitter. Okay, now, we need to find the currents. Okay, as we see here, we're dealing with a transistor. Recall the relationships IB, IC, and ID. I'm sorry, I forgot to write our beta here. So beta would then be equal to 50. Okay, for this case. So our beta would then be equal to 50. So we have beta is equal to 50. We know the relationship of these three. We solve first for our IB, IC, then our IE, rather. Okay, not ID. Okay. IB, IC, and IE, so that will be emitter current. Okay. So, we know the relationship for IB and IC, that's simply equal to beta IB. And then for IE, that's equal to IB quantity beta plus 1. Okay. So let me write it here. So IC is simply equal to beta IB. We'll be needing that later. And IE is equal to beta plus 1 quantity IB. Okay. Now, Let's apply circuit analysis here. Let's try to loop all of this from here up to here. And if we're going to loop this, we'll have Vin minus the current IC, RC, minus the Zener voltage 12 volts, okay, is equal to 0 by Kirchhoff's voltage law. Okay. Now, we have Vn equal to 20 volts minus RC is still unknown. We have RC equal to 200 ohms. And we have 12 volts equal to 0. Okay. So, let's manipulate the equation so that we'll find one unknown, IC. Okay. So, that would be negative IC, okay, is equal to, okay, or rather let's transpose IC instead, okay. So that will have a positive value for IC right away. Okay. So we have 20 volts minus 12 volts is equals to IC quantity 200 ohms. Okay. Cross multiplying 200 ohms. Okay. Introducing 1 over 200 so that that will be transferred to the other side. So we have 20 volts minus 12 volts over 200 ohms. That would equal to our unknown parameter IC. Okay. So that by solving all of this, so we're going to have 8 volts over 200 ohms, and that would be our IC, which is then equal to 36.4 milliampere, and that would be our IC. So, okay, so we've solved for our IC, that's 36.4 milliampere, but this is not the IC I'm mentioning here, okay. So for this case, this IC is only IC within here, okay. So we cannot directly relate this, but rather, we can use IE here, and we know that IE would then be equal to beta plus 1 IB, or technically IE is approximately equal to IC, okay. Okay, or the real IC. Okay. Now, to find our Zener current, that would be equal to our, okay, real IC, okay, minus our IB. And we need to solve for that one. Okay. So to solve for that one, so how do we find that? Okay. So the real IC will be within IE. Okay. So we know that if we're going to utilize this circuit, okay, we're going to say that IE would then now be equal to, okay, the voltage output divided by the load resistor, okay, RL. Okay. And that would give us, okay, so this equals to 11.3. Okay. 11.3 or 11 point? Yes, 11.3 volts. Okay, that's what we solved here. Divided by our RL, which is equal to 1 kilo ohm. Okay. And this will give us, okay, 11.3 milliampere. So we've now solved for our IE. Okay. So let's now utilize this, okay, to solve for our IB. So to solve for our IB, okay, that technically this is also equal to the real IC. Okay. So that would then be equal to 11.3 milliampere divided by our beta 50. Since we know that beta IB is equal to IC from this equation. Okay. So, cross multiplying beta here. Okay, so we have here IB is equals to 11.3 milliampere divided by 50. And that would give us 12.6 microampere. Equating this with here to solve for our Zener current, okay, so that would then be equal to 30. So that would then be equal to 36.4 milliampere, okay, minus 22.6 microampere, which is technically also equal to 36 milliampere rather. So, do you have questions, clarifications with regards to this problem or this topic or this lecture? So, if you have problems, you have clarifications, you need to clarify things, don't hesitate to send me a private message.